This project hobby I started last year. I gave a presentation at CodeBeam here a few months ago, and I'll give it again here and go over. What I was doing was trying to just start collecting some sensors, and then I wound up building more of a weather station out of it, and then I wanted to have it solar powered so I didn't have to ever run it off our outlets. So I'm going to talk about nerves just a little bit. For brevity, I'm going to kind of quickly go over what that is. I'm going to talk about the sensors and the different protocols. And then there's a few libraries you have to pull in to work with that in Elixir. Kind of what it looks like all together. There is part of this is just the nerves project I'm making. That's a physical thing outside my house. And then there's some stuff that I've built, like a Phoenix project on top of that, and a separate one to handle the data to push it into a database. And I'll show you a little bit of code. Hopefully it won't be too jumbled. There's a lot here, but what I want to kind of hammer home is this isn't actually that hard to start if you've never done anything like this before. And if we have time, I can show you the data actually getting pushed up in real time to my broker that I've got hosted on a virtual server. All right, so quickly just wanted to give a shout out to this company here in the US called Voltig. They're the ones that made the solar panel I'm going to show you and the battery that works with it properly. And they work with me very well, and I just wanted to give them a shout out because I had to go back and forth with them quite a bit to get something that worked well for me, that would stay charged and that would charge my battery enough so that I would never have to hopefully charge it off my computer or off the wall or something like that. So they're super awesome, and I wanted to give them some love. So this is the solar panel I've got right here. It's 10 watts and 6 volts. And this was, like I said, I went through with Voltig. They make a lot of different small solar panels. I mean, some industrial size almost, but this is more for powered like small microcontrollers. So what they recommended after I talked with them was something that was about 10 watts. It's at 6 volts, although the voltage changes over time depending upon how much sunlight there is and the intensity of it. So this was about $65 US, and then I needed to buy a big long extension cord so that it would come down from my roof. As you can see, it's up there on the roof. It's kind of crappy looking, but I just zip tied it up there off of some existing structure. And then I've got this battery. So this battery is probably the most expensive thing because it's such a large battery. It can 12,800 milliamps is, I don't know, probably about 3 charges off my Pixel 3a. So you can see that it's going to hold a lot of power. And the big point about this is, you know, you can use any battery pack to charge a phone or any device like that. But what happens with these small microcontrollers, and what you typically want, is for them to draw such a low amount of amps that they are going to give you as long as battery life as possible. The problem is if you buy a battery pack from, you know, some random store that's not very sophisticated, a lot of times they'll turn off so that they will preserve the battery life if they see that the device is drawing a low amount of amps. So what you want is, obviously you don't want your device to cut on and off based on how much power is being drawn. So you need something specific that works with this. This battery also is specific to the solar panel because the solar panel can give you a variety of voltage over the day, depending, again, like I said, on the intensity of the sunlight and how much sunlight there is. So you need to have a battery pack that either you'd have to build something yourself to regulate the voltage, or you can get something where it's just easier for me to pay a little more money and have something that a company made for you so that works with the solar panel like that. So I've got my solar panel. I've got my idea of, okay, I can probably hook something up to it. So I'm going to have a Raspberry Pi Zero W, but now what do? I want to write Elixir, right? So probably most of you have heard about nerves. This is a framework that lets you write Elixir and use all the good behaviors you get with OTP for your embedded systems. So the big thing that they give you is that you use their tooling to build root-derived Linux. So what this means is that the firmware that you generate out of this is a complete Linux OS, but it's extremely small, like on the order of like 25 to 30 megabytes, depending on how much dependencies you need to pull in for your project. And then there's a framework. Obviously, you get your standard Elixir library, but then they have some other tooling for you to do some special logging and test network connectivity and things like that. So I mentioned firmware, and if you're not familiar with nerves, you may think that, oh, well, I need to be able to persist data, between builds. I'm going to update my firmware as I update my code, right? But I'm writing data, I'm collecting sensor data, and if I'm not pushing it somewhere, I probably want to store it on the device, but I don't want that to be wiped out when I update the firmware. So there's obviously a partition available for you to be able to write that. But what this means, though, is your firmware is your code that, and combined with Linux, and it makes a release, OTP release under it. You can have a fallback. So it kind of is like a blue-green deployment. You can have your A and your B partition for the firmware. And if you're updating to B and you lose connectivity or something happens or it doesn't go well, it can fall back to your A state, so that you don't have to worry about retrieving your device and fixing it if you're doing this over the air. And as a company, we typically, it's very rare because you take a lot of steps to prevent this, but you can brick a device, and if it's in a very remote spot, that's a huge pain to go send somebody out to physically retrieve the device or the SD card that's on it to be able to get it back into a good state. So Nerves handles this all for you right out of the box. It's really awesome. So this is kind of what I was talking about in terms of you write your code, it'll generate an OTP release for you. It'll bring in the Linux, some C libraries, and the Erlang runtime. And then you target your system based off the architecture. So I'm in my project using a Raspberry Pi 0W, so I get Wi-Fi. So you specify that as RPI 0. All the Raspberry Pis are supported. A few things like Beaglebone are also supported by the awesome Nerds team that maintains the project. And this all gets packaged into a firmware bundle. And once you initially build your project, you can just take your SD card and plug it into your laptop or your desktop and burn it on there. After that, once you set up SSH, or they even have a nice project called Nerves Hub now, you can do this over the air as long as your device has network connectivity. So you never have to get out of your chair to do that, which is awesome. So, okay, so I've got Nerves. I got an idea that I can write some Elixir. All right, now what do I want to do, though? I started out with thinking, well, I want to collect some weather data, but what does that mean? I want to collect like temperature, humidity. I eventually found a rain gauge that I'll show you, but how do you interact with that? So there's different protocols depending upon the sensor you buy. One of them, and this is the most simplest way of looking at it, is using general purpose I/O. So you either are going to write or read from a wire or a pin. The voltage, this is something important to keep in mind depending upon what you're doing. The pins and for GPIO and Raspberry Pis operate at 3.3 volts. So this means that if you get a sensor, most of them that are nice can operate between 3.3 and 5 volts, but some don't. Some just operate at only 5 volts. So like there's ultrasonic distance sensors if you want to measure distance to something. Those operate at 5 volts, so you have to use a voltage divider using a couple of resistors on a breadboard, or you solder it. I just bring this up to keep in mind because if you use something that's 5 volts, with the Raspberry Pi, you may screw up your Raspberry Pi if you don't use a voltage divider. So when you write to it, anything near that 3.3 volts is considered binary 1, anything near ground is binary 0. And vice versa when you're reading. Anything high is 1, anything low is 0. So the circuit's got to get closed. So there's this concept of using resistors to pull the read high or low when the circuit is closed. You can either do that with using resistors and how you hook things up between either the voltage or the ground, or the nicer ones have this already built in to the sensor itself, and you just have to set it. And I'll show you what that looks like later with some code examples. So the thing I'm using with GPIO right now is this tipping bucket rain gauge. I wanted to see how much rain's falling at my house, and I needed to be able to measure that over time. So what you commonly find that's cheap is this thing where it lets us known amount of water fall in, and this is common for rain gauges, but what happens is there's a little scale, and I'll show you some pictures here, that'll trigger an interrupt once a known amount of rainfall occurs. Is accumulated, I should say. So, and this, for the device I have, is 0.2794 millimeters. It's a very exact measurement. So in US measurement, it's about 0.011 inches. The really cool thing about this is it's super easy to extend, like the one I have had about a 10-foot cord on it. It's an RJ11. It looks like an old phone cord. So I can get like some just basic extenders to connect like a female to female to connect two male ends for a cable and wire way around my house. The company I bought for doesn't sell it anymore, but it was about, I think, about $20 after shipping. Some can be cheaper and some can be more. If you look online for typical bucket rain gauge, you can find places to purchase them. So this is what it looks like on the left with, you can see the exterior I pulled off, and then there's the rain gauge there in the middle. So you can see how it's tipped to the right, and once it's tipped to the right, it'll let water fall onto the left side, and then it'll tip to the left. And for you to be able to use without pulling off the jack, I got a Breakout board. It was a few dollars online, and then I use one pin for ground and one pin for the GPIO pin to read data. And on the right, that's what it looks like up on the roof there. I didn't want to like hammer it or nail it in because I may need to retrieve it later. So I just kind of shoved it up there with the brick. It's kind of, crappy looking, but this is all hobby stuff, so who cares? That's how it looks like up there on the roof and from the top. You can see there's kind of a canonical shape that lets water fall down. And like you said, whenever you get it, you'll know how much water it takes to fall through there to cause an interrupt. So you can measure the number of tips over time to calculate how much rain is falling. So I've got a tipping bucket rain gauge, that's cool. But I want to measure some other stuff like temperature and humidity. And I want to calculate the dew point, or I may want to get barometric pressure. So those kinds of sensors that you find online use the I2C protocol. This is like a bus, so you're not using a bunch of different pins for each of your sensors on the Pi itself. What you do is you get two pins on the Pi, one for the clock and one for the data, but the sensors themselves have an address. You have to figure this out. You can find it on the sensor. If not, you can hook it up, and then there's a simple command you can run to figure out what the address is. It'll be like a hex code, like 0x77 or something like that. But this means I can still use multiple I2C sensors though. As long as they have a different address, I can just connect them on a breadboard to those two pins, and then they'll respond to the bus master. A common way of what you do with this is not writing a bunch of ones and zeros and reading a bunch of ones and zeros, is you actually write blocks of binary data, and then you typically will read them. What's really cool with this and nerves and Elixir that makes it very easy to handle is that you can do pattern matching on this. So I can say, hey, instead of reading 4 bytes, discard the next two, then I'll read the 4 and discard this one, or get the check, like at the end there may be a checksum or something like that. I can just pattern match on this, and I'll show you quickly at the end what that looks like. So it's really awesome to do with Elixir. The other thing with I2C is this kind of bit me in the heel when I was first trying to learn it, is there's this concept kind of the direction of the data almost. It's called Indianness. So they talk about does the most significant bit or the least significant bit come first, because that's what you need to handle. You need either the least significant bit or the most significant bit. If you look at a data sheet, it'll reference that. So what you'll find is that there's the concept of big endian, which means most significant bit first comes first, and little endian, which means least significant bit comes first. And that just is relevant for how you calculate some measurement or something like that, or interact with the device. So this is what the Raspberry Pi, I think every single one almost looks like this, except for maybe some very early versions of the very first Pi. So you have different power pins. Even though you may see 3.3 volts and 5 volts here, though all the rest of the pins for GPIO and stuff that you're reading onto or writing from operate at 3.3 volts. But some sensors need to be powered at 5 volts only, like the distance sensors, so you can at least get those powered properly. So you see there's the 2 I2C at the top. There are some down in the bottom middle there, but those are not, you don't get access to those. I believe they're for peripherals like hats and things. And then there's a bunch of GPIO pins. There's SPIs, another interface, as well as UART. So you get a lot of pins, and this is handy as guide is at pinout.xyz, because depending upon the library you're using, the pin numbers may be different. So you can go to here and click on it in each of those pins and see what the number is depending upon which library you're using. So my sensors that I'm using that are I2C are one I had from just a while ago. If you bought it now, it'd be like about $6 US, depending on where you get it. It's this old BMP 180. It's an older version of a model that's been updated. It's probably a little less accurate, but this will at least give me barometric pressure, and it also collects temperature. But I wanted to see humidity as well because I wanted to calculate the dew point, and I need temperature and humidity to be able to do that. So there's lots of sensors that do this, but the one I bought was about $9 US. It's called the SHT31-D, and this will give me humidity as well as temperature. And this is an example of how, like with the BMP 180, this looks kind of daunting. It's actually probably the most straightforward without trying to use like a NIF or something that's written in C or Python. You, just as an example, this is kind of what you have to follow. This was very scary to me because I couldn't find an Elixir library that was already made to use the BMP 180 or an example of using a NIF. So I had to go through this process. There's a bunch of other steps down here, but this is kind of what you need to do. You have to, a lot of times, read the calibration data. So as an example here, they show you what these numbers look like. But on your sensor, these will probably be a little different. And that I guess it's calibrated at the time the device is made. And that's going to be useful to be able to read the temperature and barometric pressure. So you go through all this bitwise math. You can see here, you see, read register 0, F6, so that's most significant bit. And the other one's least significant bit. So this is like the concept of the big and little endianness that you have to look at. All right, so I've got my sensors. I've got an idea of maybe how to work with them. But how do I write Elixir code so that I can interact with them? So there are these libraries that used to be all in one thing called Elixir AL, but probably I guess it's been a little while. They've broken them out into a library for each of the protocols. So I'm going to pull in circuits and then the GPIO library and one also for the I2C protocol. You don't have to use these with NURBs. And in fact, when you're prototyping your stuff, like I showed you a picture earlier of my tipping bucket rain gauge with the Pi, I don't want to have to make firmware and push it onto the device and see if everything boots up properly. I just want to be able to take like Raspbian or some OS that you can burn on an SD card and test it. So you can just pull these into Elixir and you can start interacting with the sensors that way. And then later on, you can make a NURBS project out of it. The quick thing I wanted to mention with GPIO is that you'll get a timestamp. You can set to listen for interrupts, and then you can look at timestamps on them, which wasn't available in this Elixir AL library before. And this is useful to calculate time between rising and falling edges. So for certain sensors, you may want to see when something first triggers and then the next thing triggers, and you need to be able to calculate the time without trying to do a bunch of sophisticated code. It'll actually give you a timestamp on it, and you can measure the differential between those to, I don't know, calculate how long something took. The libraries are really awesome and easy to use. All right, putting it all together. This is what my, this looks really crappy because it's just a project. I don't have a 3D printer, so I just bought some Tupperware and I cut some holes in it. You can see the breakout board I've got with the white cord there for my rain gauge. The orange cord's my charging cable coming from the solar panel. There's the battery. There's a breadboard, so I can have multiple I2C devices on it. And then there's the Raspberry Pi Zero W down at the bottom there. So this, again, this looks all crappy. I've kind of made it look a little better. This is an old picture. But you can see the solar panel there at the top. This is around the corner of my house. And then here's the white cord is the tipping bucket rain gauge. The important thing when you're measuring temperature is you need to have it in the shade. So initially I had this on another side of my house where there's a lot more shade, but because the panel didn't have enough sun, because there's a lot of tall trees, pine trees here in Georgia, that wasn't charging the battery enough. So I had to kind of put something together so that I could at least shade it. So, you know, it's not perfect, but if you want official temperature, you need to have the sensors in the shade to be able to give you official temperature that is used for reporting and things. So here's the first part I've talked about is everything on the left. So the NURBS weather sensors is the little NURBS project I made. I won't belabor the point, but I'm just showing you what I'm doing is publishing that data. So I'm not writing it to the device. I don't care if I miss a publish or something like that if network connectivity is down, but I need a broker. So what you commonly use in IoT stuff is MQTT, is a protocol to send out little bits of data, and you can use a pub/sub method with brokers. One of the easiest ones to use is Mosquito. It's a Python library, but you can very easily install it on an EC2 instance I have with my personal AWS account. And then I can easily set up other things to subscribe or to publish to that broker and set up some basic authentication. So the weather station project there down at the bottom is a Phoenix application I have to look at my data in real time and also historically. The database application I have up there in the top middle is just a separate project I had that handles all the data getting shoved into the database, as well as running a job daily to back it up, push it into an S3 bucket. All right, so let me show you the code. I'm gonna have to see if I can share this real quick. Give me a second. Let me share another thing here. I'm going to show this. Okay. So if you can see my screen here, this is some just relevant code I pulled out into a folder. So the first thing I've got right here is trying to work backwards, I think, is the easiest way to conceptualize this. This is on my Nerves device. I've got a couple of libraries I wrote for the SHT31 and the BMP sensor. I need to get some references, and then I'm going to start this range server. And the idea is I need to be able to look at the interrupts as they happen, but I don't want to, every single time an interrupt happens, I need for it to store some state. So I'm going to wrap it in a gen server. And I'll show you that in a second here. But this is all just stuff. I'm collecting the data, I'm formatting it and rounding it, and then I'm publishing it to that broker on the topic of this topic right here, the front/temp humidity dew point pressure. The first thing is weather sensor. That's the client ID. That needs to be unique if you're using the broker. So I need a unique client. That's my sensor, my Nerves device. Tortoise is just a really easy to use library that lets you work with MQTT. And then I'm logging some data. And then the idea here is I'm scheduling this once a minute, but I need to happen. I don't want a bunch of drift. Because if I just did it, say, hey, send it in a minute again, it's going to start drifting over time, and I may have something where I've got two measurements in the same minute, and then it skips a minute or something like that. So that's what I'm doing there. So the SHT sensor, I don't want to go into all the guts of this. This is just basically you read the documentation or you find some examples online. This is how you use the I2C protocol to get some data out of it. So I just have two different functions here to give it in Celsius and or if I get it in Fahrenheit. Same with the BMP 180. It's a little longer. You have to get this calibration data and you do all this stuff. Here's Big Indian stuff that I was talking about here. You do a bunch of, I showed you with the data sheet, a bunch of bitwise math and things like that. And eventually I've just got some functions down here that I'm just going to say, hey, read pressure. I can calculate altitude from the barometric pressure. I can read temperature, and so on and so forth. All right. So that's a little more complicated looking, but it's a lot more straightforward, I think, once you start looking at how you work with these sensors. The other thing I've got is the range server. This was that GPIO sensor, and I talked about needing to see interrupts. When the bucket tips, it's going to trigger an interrupt, and I need to catch that, right? So what I'm going to do is I'm going to wrap this in a gen server. I'm going to get my pin that I need. I'm going to set as input. And then based on the documentation, I need to set this as a pull-up, pull-up resistor, whatever. You understand what I'm saying. Sorry, I'm getting confused here. But anyway, I'm going to schedule a collection, which means I'm just going to say, hey, I want to start looking for the data to come in. And I'm going to just give it some time to set up, and I'm going to start the handle info callback will say, hey, what's the rainfall? Well, what I'm going to do here, and this is the important part right here, is I'm going to set to listen to interrupts, but I only want to see the falling edge. You can set rising, falling, or both. And this means I'm going to get a message to the mailbox in this gen server. So I need to receive, and it's this pattern right here. And that means when this gets triggered, that amount of rain is falling. Otherwise, I need to yield every so often so I don't just continuously block the gen server. After 2 seconds, I'm going to say, hey, 0 rain has fallen. And I've messed with this enough that I don't think I'm going to miss any tips. If I say, hey, after 2 seconds, say 0 and then schedule and go again, I'm pretty confident that I'm not going to miss any rain this way. So going back to the weather server real quick, that was what this is. The rain server, I'm going to start a link to it. And then I'm going to get the rainfall there. All right. Let's see, which one was this? This is my, this is just using Tortoise here to set up the connection to the broker that I've got running in an EC2 instance. I've got it all set up as application environment variables and then the client ID here. So the other thing I want to show you is the 2 different projects I've got. This is just part of the code for my database handler. I'm not going to show you the backup job, but I'm going to use Tortoise Handler. You set it up so that you listen on a topic, and I'm going to look for this specific topic, right? That's the formatted data that I showed you that the sensor is pushing out. I'm going to just do some other stuff to get some conditions from an open weather map API. And I'm going to just get that, and if I don't get it, it's fine. I'm just going to say it's nil, and then I'm going to insert it into my database, all right? And then this is just a message that if you subscribe to something and you don't have a catch-all, it'll crash. This is in the Tortoise documentation. It says to do that. So that means when I publish to the broker, this is going to get triggered. I'm going to shove a row into a database that I've got set up. And this is the same thing. This is the back-end part of my Phoenix project, right? So I've got the same thing here. This repo is just an ETS table because when I hit up my view to see the live data, I don't want to necessarily always have it hitting the database. I can just store it in an ETS table. It's not a big deal. And I'm going to use PubSub with Phoenix to broadcast that some data is coming, and I'll show you why what that means in a second. Actually, this view. This is a live view I've got in my Phoenix applications. This is on the client stuff here. I've got all these, they've got the dew point, the humidity. I've got 2 different temperatures, barometric pressure, the conditions from that open weather API. And I'm going to, if it's connected, subscribe to that PubSub that I was showing you earlier just a second ago that's going to publish to this. Otherwise, when you hit the view, I can just look at that ETS table here. That's what this repo is. It's just hitting the ETS table and getting that latest data. There's some old crap in here, but this is just, I'm assigning it to the socket. And then when when that weather update PubSub event happens, I can say, hey, put the data that I just got from you onto the live view. All right. We should have enough time here. Let me, once again, stop this. I'm going to share the browser. And this is what my live view is, right? So this should happen. You'll see it change here just in a second. Okay, there it is. So that's the live view. I've got this hosted as a Phoenix application, literally just outside the house here. That thing pushed up, hit the broker. The broker said, hey, I've got this information on this topic, so publish it to anyone who's listening. I've got 2 different listeners, the database listener and then this listener right here. And that's kind of how that looks. I've built another couple of views. This is reading from the database here. And this is just using a simple charting library. This is also live view, but you don't have to necessarily use that. I was just testing it out. This will update too as data comes in. You'll see the line get changed a little bit. So here are my 2 different temperatures. Here is the humidity over time. And I've got this set up so I can go back an hour or any hour. I can go pick a day. So I think we had some rainfall that day. So let me see daily, the 15th. And I'm going to look at rainfall. Yeah, so we had some rain then. And that was at the hour of 16, so 4 o'clock. That's right. I looked at this yesterday. So I'm going to go back to hour. This is not the best thing I made, but this will be 4 p.m. here's the rain. You can see one tip. These are like, each of these is just one tip. It's 0.011 inches. And that's it now. That's basically where I'm at right now. I'm going to build a few more little views. But hopefully what I've kind of hammered home here is, this is a lot of whole big project, but interacting with these sensors, once you get kind of familiar with some of these concepts of the protocols, you have to talk to them. It's pretty easy using nerves to just write some Elixir code. And then you can just, if you have network connectivity, you can publish it to something, you can write it to the device itself and collect it later. There's a lot of different things you can do. So yeah, I'll handle questions now.
Excellent. Very interesting, very cool project indeed, John.
Thank you.
We have a couple of questions. First, was the panel and battery enough to run it 24/7 for the whole year?
Yeah, there's a whole backstory to this, but basically, at least during the summertime, I have not had to charge the thing. During the wintertime, when we've had a lot of gray skies, there has been a couple of times where I needed to pull it out and charge it, and I'll just swap the battery out with another one. But I'm been pretty, it's like 99%. It's up a lot. So I initially had a smaller panel. I had it in a different place. And then I figured out, well, let me just put it on the roof because that's probably where I needed to get the most sunlight. I was also having to talk to my wife because she's very opinionated about the aesthetic of the house. So she didn't want this to be really obvious and ugly because this is not like flat on the roof. I needed it pointed at an angle to get as much sunlight. So yeah, I'm pretty close to about 99% availability on it.
All right, good. Another one, what charting library did you use?
It's called Chart.js. I've got it with a bunch of hooks with the live view. Chart.js was probably the easiest one I found. The really cool thing I've seen people do that have more experience with SVG, they'll just use SVG and write their own charts. But Chart.js is a pretty easy library to use. Pie charts, bar charts. If I look at monthly here, I've got some bar charts for my highs and lows. So this is all easy to use, yeah. Chart.js.